Thank you. I'm Carlos. I'll start with a little bit about myself. I'm an embedded software engineer. I worked in a couple of different industries, from rather small to rather large embedded devices. Now I'm very happy to work for the Microbit Educational Foundation, where we aim to inspire and enable the next generation to create with technology. My academic background is actually in electronics. There you learn to design circuits and program in languages like C and C++ at the same time. So it's very easy to see the correlation between the code that you write and what's happening on the hardware. We all love Python, but like with any other higher level language, there is a little bit more distance between these two things. So my aim for this talk is to cover what happens in the lower layers. What's MicroPython? Well, it's a lean and efficient reimplementation of Python 3. It's been created by Damien George, and it has been designed from the ground up to be efficient in memory-constrained devices. It can run in things as small as 16 kilobytes of RAM and 256 kilobytes of RAM. This is tiny, and the really cool thing about MicroPython is that it's able to pack the parser, the compiler, and the virtual machine. While Python very famously includes batteries, MicroPython has to be a little bit more conscious about the kind of things that it can fit into the device. So batteries are not included out of the box, but they're very easily installable. And it's available in a wide range of platforms. This is a very small sample. We have things like the Microbit, the PyWord, the Secret Playground, and on the top right we have the Raspberry Pi. Now the Raspberry Pi actually runs CPython, and then it uses libraries like the awesome GPIO0 to interface with hardware. But the reason I bring this up is because a lot of the things that I will cover in this talk are not specific to MicroPython. They apply to any Python implementation and even any other language. Right, so let's say you have your MicroPython board, you had some time to play with it, to do stuff on the REPL. What can we do next? Well, we can add some electronics. And this is when the fun begins, because it enables you to expand the capabilities of the boards and to do more things in the real world. We can use modules like the one shown on the left, where you can very easily plug in cables and get going, or you can create your own circuits. If we are lucky, maybe there's already MicroPython libraries in PyPI. In that case, we can use something like MicroPyp to install them or copy the files manually. But what happens if there are no drivers or something doesn't quite work? Well, I might be a little bit biased here, but I think that's when the real fun begins. But before we get to that, let's try to find everything that we need first. First, let's try to find a driver. You can basically just get the part number, put it in Google, and then put the word Python or MicroPython. Hopefully, you should be getting some results that way. But if Google is your best friend, GitHub is your best friend. You basically just put the part number in GitHub. You can filter via Python language, and you should be able to get some results that way. If you cannot find any MicroPython libraries, make sure you look at other languages, because they're great for reference. But let's not forget to look at the official documentation. This is because if you go to the manufacturer website, you'll be able to find the datasheet, which is the main source of documentation for your electronic parts, but also application notes, white papers, and reference implementations. OK, so now we've got all the info that we need. But how does writing some code actually make something happen in the real world? Let's look at an example. This is a constructor for an accelerometer driver. It starts by initializing something called an I2C device. Then it reads some data and compares it against a magic number. Then it looks, it writes something, it immediately reads that back, and then in a loop it checks if that value has changed. If this is the first time you're seeing something like this, it may be a little bit confusing. So let's take a step back, and let's look at the software stack. At the top, we have our Python code and our Python modules. They are interpreted and executed by MicroPython. MicroPython in itself, it's written in the C language. And within MicroPython, we have something called the hardware abstraction layer. This is where the hardware magic happens. These are libraries usually provided by the microcontroller manufacturer that let you control the hardware. In this diagram, we can see the microcontroller in the green box, and inside it, there's a lot of smaller boxes with weird acronyms. These are the peripherals. The peripherals are blocks of circuitry inside the microcontroller that are in charge of a specific hardware feature. What this means is that the peripherals let you control other things. So we can use them to talk to sensors. We can use them to read from a microphone, output sound in a speaker, write to an SD card, move a motor. But how do we control these peripherals? First, let's look at the memory map of the device. This is in the datasheet of the microcontroller, and it tells you where different things live in memory. Here we can see that the code lives between these two memory ranges and the RAM immediately above that. But the most important thing for us right now is the peripheral. And it's telling us that the peripherals live between that memory address and that one. We look at the peripheral documentation, and we find a table like this one. It's a bit small, so let's zoom in. What this table is basically telling us is that for each peripheral, there is a memory address that you can use to control it. Let's take an example. Let's look at the GPIO. When you connect an LED to your board, generally you put it into a pin, and the pin is controlled by this peripheral. It's the general purpose input and output. So we look at the GPIO peripheral documentation, and we find another table. In this case, this is a register map of the peripheral. Each register, it's basically a word in memory inside of the microcontroller, and it's in charge of a specific feature within the peripheral. This table will actually tell us the memory address offset form within the peripheral. So we are able to calculate the exact memory address of the peripheral. Let's look at the out register first. We look at the documentation and we find yet another table. In this case, the register in this architecture is 32 bits, so we find 32 columns in the blue thing at the top. We also have 32 rows below it, but I've cropped the first two for clarity. Let's say we've connected an LED to the pin 0. In this case, pin 0 is represented by the first bit, and what this table is telling us is that when you write a 1 into this bit, the pin is going to go high, and that's going to turn on the LED. And when you write a 0 into the bit, it's going to the pin driver is going to go low, and it's going to turn off the LED. And that's really all you have to do. You read and write to the right bits in the right register from the right peripheral. OK, so now we know how to control a microcontroller. But maybe I have an external sensor. How do I control that? Well, there are mainly two methods we can communicate with electronic devices via electrical signals. We can use analog or digital signals. For analog signals, the information is usually represented by the amplitude, the voltage amplitude. So we measure the voltage at a point in time, and then we apply a meaning to that value. On the other hand, digital signals have two discrete values. When the voltage is high, it represents a 1, and when the voltage is low, it represents a 0. These days, more PCBs, motherboards, and most of the modules that you will use probably communicate using digital signals. So we're going to look at 3 digital protocols. The first one is UART. It stands for Universal Asynchronous Receiver Transmitter. Basically, you have 2 devices, and you connect two cables in between them. These data signals are unidirectional digital serial data lines. What that means is that the data flows in one direction, one bit after another. The baud rate is the frequency at which the data is being transferred. And in this case, it's the system designer that has to configure it. So it is your task to make sure that both devices are configured the same way. Let's have a look at the actual signal. When the data signals are idle, they're not doing anything, they will rest high. And then for each packet or data frame, you start by following this format. You first send the start bit, so it pulls the data log for 1 bit. Then you send 5 to 9 data bits. Then you can send an optional parity bit, which is for error correction. And then it ends with 1 or 2 stop bits. And what does this look like in code? Simple as well. We import the UART class, we initialize an instance, and we pass as constructor parameters the settings we need to configure. Then we can use simple methods like read and write to get data from and to the device. The next protocol is the SPI protocol. It stands for Serial Peripheral Interface. In this case, this is a synchronous serial protocol. Basically, we have a master device at the top, and then we can have 1 or more slave devices. This protocol also has unidirectional serial signals, just like UART. One is called master out slave in, MOSI. The other one is called master in slave out, or MISO. In this case, we also have a clock signal. Before, it's the system designer that has to specify the settings. And in this case, it's the master that detects the frequency at which data is being transferred. So right now, we have 3 signals that are shared between all of the devices, but there is also a 4th one called slave select. We need 1 signal per slave. So in a configuration like this one, we would need 1 master out slave in, 1 master in slave out, 1 clock, and 3 slave select pins. So let's have a look at the waveform. There's a few more things going on, but it's not too complex. Let's just start with the bottom one. When the master wants to initiate a transfer, it will pull the slave select line down, and then it will immediately start sending the clock and the data. There is no start bits or stop bits. It just kind of slave down, data out. When it's done, it will stop sending the clock. And then if the slave device has some data to send back, it will do that in its own data line. Remember that the clock is still controlled by the master, so it's in charge of configuring the data speed. And the Python code is very similar to the previous example. We import the SPI class, we initialize an instance with the right parameters for the constructor, and then we can use methods to send and receive data. The last example is the I2C protocol. It stands for Inter-Integrated Circuit. This is also a synchronous serial protocol. So we have one master and one or more slave devices. But the main difference here is that we only use 2 signals. Doesn't matter how many devices you've got, you only need 2 cables. And the way that the master can target each slave is because they have individual IDs or addresses. So let's have a look at the signal. We start by the master starts by pulling the data line low, and then it will start sending the first byte and the clock at the same time. Now, from the first byte, the first 7 bits are the ID or the address of the slave. So it's basically saying, device number 3, I want to talk to you. And the last bit from the first byte, it's the read or write command. So it's basically telling it what it needs to do. At that point, the master has to drop control of the data signal. And then the slave can acknowledge that it's received the right data and knows what to do. If it needs to send some data back, it will do it at that point. And then when it's done, it will drop control of the signal, and the master can acknowledge that it's received the data. And how does this look in Python? Well, we import the I2C class, we initialize an instance, and then we can use methods like read from, giving it the slave address and how many bits you want to read. Okay, so now we know how to communicate with external sensors, but how do you know what to send or what to receive? Well, we just read the documentation. And in hardware, the documentation are datasheets. Now, I must confess, the first time I read a datasheet, there was quite a few things that I didn't quite understand. And this is fine. Like, being able to effectively read a datasheet, it's a skill that comes with time and experience. So one of the things I want to do here is kind of like give you a general introduction of to what to expect, the kind of things that you should probably be reading, and the things you can probably skip. So we go to the manufacturer website, and we find the right document. This is for the accelerometer I mentioned before. We download a PDF file, and this one is about 60 pages. So that's not too much, it's not too little. We open it, and the first page is I generally call it the marketing page. It gives you a general overview of what the device is capable of. So it's really important to make sure you read this one to know what you have. Then we can find the index page. And this is also important because while a lot of datasheets will give you the same kind of information, they might present it in many different ways. So being familiar with the index can give you a general view of what the format of the document is. In this specific case, there'll be a couple of pages that talk about the physical package of the device, so you can skip those. Then we have like 5 or 6 pages full of tables with numbers, voltages, current, signals, and stuff like that. That's generally targeted for the hardware engineers, so you can probably skip this as well if you're only interested in doing the software drivers. Then we find about 10 or 12 pages of blocks of text. Sometimes you find this many, sometimes maybe a few less. And this is basically giving you the general description of how to operate with the device. It's very important to read this, but perhaps you don't have to read everything. A lot of the times you get a device that has a lot of different features, but you may be only interested in a single one. So read the introduction, read a section that talks to you about how to initialize the device, and then just read about the sections that you want to implement. In this case, then we had a page that basically it's telling you how the I2C protocol works. So if you already know that, you can skip it as well. Now we find the register description. This is a list of registers, and it's very useful because they give you like short descriptions of what each one of them does. If you've read the previous section, you should get a good idea of what you need to read from here, but having this, it's very useful as well. So we look at a random register, and we find a page like this one. And this should look familiar because it's a very similar format than the microcontroller. It's basically a register inside the device, and this page is telling you what's going to happen if you read or write into that specific register. And we get a lot of them. So just pick and choose the ones that you want to read about, or the features that you want to implement. Or if you have trouble sleeping, just go ahead and read the entire thing. And the last few pages are basically mechanical characteristics of the device. So unless you're making your own PCB, you can probably skip this as well. OK, so now we have all the pieces that we need for our driver. Let's look back at our earlier example. The code is exactly the same, but now we have the tools to understand what's going on. We can see at the top that it's initializing an I2C class. Then we see that it's reading a register and comparing that with a number. We don't really know what that is yet, but we know how to find out. We go into the datasheet, and we look at that register name, and we find out it's called the whoami register, and it gives you a device ID. Basically, what this is doing is checking that you are talking to the right device. We go into the next block, and it's writing into a register and reading it back, expecting it to change eventually in a loop. So we go back into the datasheet, and we find out that writing to this specific bit, it's going to reset the device. And that bit is going to be set while it's resetting. So that loop, all it's doing, it's waiting for that to finish. And then underneath all of that, we basically have normal write operations. Just like before, they write to specific registers to do some configuration. And we can go back into the datasheet to figure out what's happening. So in the end, MicroPython driver code is not all that different than your average Python code. We just have a slightly different documentation. But there are a few things we need to keep in mind. Now, I didn't want to go into too much detail about this specific area because there's a lot of great talks online that give you a lot more tips and just general good advice on how to write efficient drivers. But there's some things that you'll often see in most drivers. The first bullet point is actually something specific to MicroPython. If you have something, if you're storing a value into a variable that doesn't change, that it's a constant, you can use the const keyword or function to actually let the compiler, the MicroPython compiler, optimize that. The ustruct module, it's very, very useful because it's going to allow you to pack and unpack variables from blocks of binary data. So when you're getting data from your sensor, you can use this to make sure you easily put that into the right variables. As you've seen, we talked a lot with registers. We configure registers, so bitwise operations are very, very common. You want to make sure you manipulate specific bits on bigger data types. Because we're using very small devices, we have to be very careful about memory allocations. Even if you're using temporary allocations when you're creating new objects or things like that. And this is because it's very easy to get memory fragmentation. So even though you might have still plenty of memory available, because it's fragmented, maybe you won't be able to save bit objects. One method to do a good memory management is to do buffer pre-allocation. So in your drivers, you make sure you allocate a single buffer, and you can reuse it every time you read and write within your driver. If your driver is rather large, you might hit some memory problems eventually. And you can use the garbage collection and the MicroPython modules to control the garbage collection and to be able to do a little bit of memory profiling. So you can see how the memory changes over time as your application runs. But most importantly, have a look at the documentation, because the MicroPython docs have really good articles telling you the kind of things that you might want to do for this type of applications. OK, so you have your driver, you finished, you think it's going to be great, you load it, and something doesn't quite work. What do we do now? Well, we can start debugging. But the thing is, debugging in hardware is slightly different than debugging in software. There's a few more things you need to keep in mind, and there's a few things that are going to work differently. So I'm going to go through some of those differences here. The first thing you should do is to check all connections and power supply. This is very important because it's very easy to make mistakes. The second thing you should do is to double check all your connections and power supply. Believe me, I've wasted so much time just to realize I didn't turn on the power supply. So make sure you check. If you have multiple devices or sensors or modules, make sure they share a ground. And in the same case, make sure that they have the same logic levels. They may be speaking at different voltage values, so you want to make sure that they're all at either 3.3, 5 volts, or whatever they are. When you're trying to communicate with an external device or a sensor, and it doesn't quite work, the first thing you can do is to reduce the data speed. And this may actually get you talking to it, even if the data is not quite right, and it can help you figure out what the problem may be. And this is just general good practice. You should find the simplest possible code example to replicate your problem. That's really going to help you figure out what's going on. You should then go back into the manufacturer website and search for application nodes and other implementations, because sometimes some of the information that you need from the datasheet may be buried somewhere that you haven't looked. So having those reference implementations, it's very, very, very useful. I cannot really emphasize this enough. Go to GitHub, look at other implementations, see how they've done a similar thing. And if it still doesn't work, you should search for erratas. Every once in a while, there will be bugs in the silicon. That means that you've done everything right. It's just the chip doesn't quite work. They should actually include workarounds. To be honest, you wouldn't believe how many times the workaround is don't use this feature, but putting that aside, it's good to know if there's any problems with the chip itself. But the most effective way to debug is to be able to capture and retrieve the data that you're sending down the wire. There's a few methods you can use to do that. You can use the classic print debug. In this case, you probably need to use a UART driver and something like a UART to USB bridge, and you'll be able to connect your device to your computer and get some data out. But you can also use hardware debuggers. Now, hardware debuggers will let you step through your code and put breaking points, but you have to keep in mind that you are actually debugging the MicroPython source code in C. That still can give you a lot of clues as to what's going on, but it's not your Python code that you're debugging. The other nice thing about hardware debuggers is that you have a view of all the memory registers, so you can actually see how things have been configured. I will cover logic analysis in the next slide. And then if you don't have any of this, you can just use LEDs. This is really the original print debugging embedded. You basically turn LEDs on and off on different points of your code, and you can see your code flow. Right, so logic analyzers. This is the kind of slide that a couple of years ago I really wouldn't put in a presentation like this, because like the first example is what I would call cheap for professional use, but still expensive for hobbyists. The thing is, like right now, because of thanks to the open source community, we have something like SIGROG, which is an open source signal analysis software. And with that, you can get signal compatible devices for as little as £10, which is just incredibly cheap. What a signal analyzer tool lets you do, it's a box with cables. You put those cables in your serial buses, in your databases, and it will actually capture the data and decode it for you. So you actually get to see exactly what's happening on the signal. This is really, really useful. And for £10, I couldn't recommend it enough. OK, so in summary, we have learned that there are peripherals inside your microcontroller that are responsible for controlling specific hardware features. That the hardware can be driven by reading and writing into these peripherals by finding the right register. We've learned about multiple protocols that you can use to talk to different devices, and that datasheets are the main form of documentation that's going to tell you how to talk to these devices. MicroPython code is quite similar, but there will be some differences. So while a lot of it will be familiar, you might have to relearn a couple of things. And I hope this is your main takeaway, because hardware is awesome, and even more so with Python. Thank you.
Thank you, Carlos. Any question for Carlos?
Hey, thank you. You mentioned micro devices not having much memory. Do you have any advice for reducing code size so that we can use more of that memory for fun stuff?
Well, especially with MicroPython, you have to keep in mind not only the memory used in RAM, but the memory used in Flash. So sometimes you may be restrained in different ways. To reduce the actual code size, that's usually the memory, the Flash memory. And this is one that I feel a little bit conflicted about, because normally you write your code and you want to make sure that you put as many comments as possible to document it. Especially with hardware, because a lot of the times you're getting data that you're writing to registers or getting magic numbers that are difficult to figure out just by looking at the code. That will take space in the Flash of your microcontroller. So what I normally recommend is to make sure you write your driver as you normally would do, and then you can post-process it just like you do with JavaScript minification, where it removes all the comments and can even change the spaces by tabs. I know, but actually a tab saves you 4 spaces, 4 characters per line, so that can still be quite useful as well. And for memory, for RAM memory, making sure you don't do temporary allocations and pre-allocate buffers is actually one of the main ways to reduce the memory footprint.
Any other question for Carlos? Yeah.
Thank you very much for that. When I built my plotter, I tried at first to do it using a MicroPython board, and it wasn't successful. I found it in the end much easier to do it using a Raspberry Pi, but originally that's what I wanted to do, and trying to maintain the libraries that would work on both just was too much work. Do you have any advice about how I might try and do that again, in the future, if I want to make it work on a Pi board as well as on a Raspberry Pi, using the same code base, is that something that I should think of doing?
Yes, absolutely. So MicroPython, when MicroPython was designed, and as it still continues to be developed, they have to put emphasis on efficiency, because these devices are very small. So they make a lot of choices that are right for that, but perhaps are not ideal for portability of code. Within MicroPython itself, like if you use different boards, some APIs may be slightly different. Some of the things may be close enough where you might get that false sense of security that you know how it works, but then some arguments are switched around. So it's good to have a look at the documentation for that type of thing. And Adafruit has actually created Secret Playground. This is basically a fork of MicroPython. And their main priority for their version of MicroPython is to make sure that it's easy to use. And apart from that, it's to make sure that it works the same all across the board. So if you use CircuitPython, the APIs will be the same on MicroPython boards, CircuitPython boards. You can install their libraries on Raspberry Pis and devices like that. So you'll be able to have a lot more code portability by using something like that.
Okay, let's thank Carlos once again.